Hello students, let us start our today's session from the chapter Aldehydes, Ketones and Carboxylic acids. Today we are going to discuss about the physical properties of the compounds and nucleophilic addition reaction, oxidation and reduction. So physical properties, it discuss about the physical state, boiling point, solubility and odor of the compound. When we discuss about the physical state of aldehydes and ketones, the formaldehyde alone exists in gaseous state at room temperature. And acetaldehyde that exists as a volatile liquid. Volatile, it can easily evaporate at room temperature itself. But all other aldehydes and ketones, they can exist in liquids or solid state at room temperature. What about the boiling point? Boiling point, we know very well, when the molar mass increases, boiling point of the compound also increases. And when we discuss about the boiling point of carbonyl compound, we have to understand about the nature of interactions present in aldehydes and ketones. We know well the carbon is doubly bonded with the most electronegative oxygen atom, and hence the oxygen can withdraw its electron from the carbon, thus creates a dipole. So this dipole, it can interact with another dipole. So aldehydes and ketones, they possess a weak dipole-dipole interaction, and hence their boiling points are greater than ether and than hydrocarbons. But when we compare to alcohol, aldehydes possess a lower boiling point than alcohol. This is because alcohols, they have intermolecular hydrogen bonding. This intermolecular hydrogen bonding is much stronger than dipole-dipole interaction. But the boiling point of carbonyl compounds lower than alcohols, because alcohols possess a strong intermolecular hydrogen bonding which is stronger than the dipole-dipole interactions too. Because of this, carbonyl compounds possess lower boiling point than alcohols, but they have higher boiling point than ethers and hydrocarbon of comparable molar masses. What about the solubility? The solubility actually has to take place only when both when both have the similar kind of interactions. So in this case, the formaldehyde, acetaldehyde, acetone, they are miscible in water. Why? Because the presence of oxygen in carbonyl group that allows to make hydrogen bond with hydrogen atoms of water. So even though the dipole-dipole interaction is present, that can be broken easily, so that can put up a strong hydrogen bond between the carbonyl group of aldehydes, ketones and the water molecule. But at the same time, the miscibility of these aldehydes, ketones decreases when the alkyl group increases, because the alkyl group becomes hydrophobic in nature, and moreover these carbonyl compounds are even fairly soluble in organic solvents like carbon tetrachloride, benzene, ether and alcohol. Then what about its odor? So already we discussed, these are more fragrant. The aldehydes and ketones are in general, they are naturally fragrant in nature. But the odor of lower members, they have a pungent smelling. Pungent means some irritating odor. But at the same time, when the higher member it approaches, the pungent smelling becomes the more fragrance. Because of this nature, aldehydes and ketones are usually blended in perfumes as well as in flavoring agents. That's all the physical properties of carbonyl compounds. Chemical properties of aldehydes and ketones. We know well aldehyde and ketone, they possess both CO group in its structure, as they have the similar carbonyl group. So both of them will undergo same types of chemical reactions. Let us discuss first of all the nucleophilic addition reactions in carbonyl compound. Why does it undergo nucleophilic addition? Because the carbonyl group is C double bond O. So the presence of the pi bond, the doubly bond structure during the nucleophilic addition reaction is converted into a saturated hydrocarbon derivative. So let us discuss about how a nucleophile approaches the carbonyl carbon. See, this oxygen atom, as it is more electronegative, it can withdraw the pi electron from the carbon and from the carbon. So as the oxygen is more electronegative than carbon, it withdraws its pi electron. Subsequently, the carbon, it gets the positive charge, and hence the nucleophile that approaches the electrophilic site of carbon. So we are getting carbon bonded with the nucleophile, as well as the oxygen gets the negative charge. So in this case, the carbon actually sp2 hybridized to 1. When nucleophile attacks the carbon, the hybridization, it changes into sp3. And the shape of this carbonyl is actually trigonal planar that changes into its tetrahedral geometry. So after that, it forms an anion because the oxygen carries the negative charge. That O minus abstract the proton from the reaction medium, we are getting OH. So the presence of C double bond O that changes into C nucleophile with OH. So this undergoes addition reaction with nucleophile. Why nucleophilic addition? Because carbon carries the positive charge and the electron density of carbon decreased by oxygen atom. That's why a electron rich group can approach the electrophilic site, and hence we are getting the addition product of carbonyl compound. Okay, how do you explain about the reactivity of both aldehyde and ketone? Aldehyde, we have the first member formaldehyde, then it goes successively acetaldehyde, propanaldehyde, etc. That means number of alkyl group increases, only it starts from acetaldehyde. But the formaldehyde, you may find it has no alkyl group, it is simply HCHO. But in ketone, the first member itself carries the 2 alkyl group. And we know well, the nucleophile usually a bulkier size. When the nucleophile approaches the carbonyl group, the presence of 2 other valencies of carbon has to allow the nucleophile to approach the carbon more easily. But it is not possible when we have ketone, as it has too bulky nature of alkyl group. So as the bulky size of alkyl group increases, the approach of nucleophile will be hindered by the presence of alkyl group. So we can say formaldehyde that can undergo nucleophilic addition reaction more freely and effectively because it has no bulky group. And acetaldehyde, it has 1 bulky alkyl group and 1 hydrogen atom. So it can permit the nucleophile to approach the carbon. But when we go to ketone, due to the presence of the 2 bulky nature of alkyl group, the reactivity of ketone decreases. So one reason we can find it according to steric reasons. The other reason also we can discuss, because it is because of the plus I effect of alkyl group, that is discussed under electronic reasons. See, once again in formaldehyde, it has neither plus I group nor minus I group. So this molecule can undergo the nucleophilic addition reaction more effectively. But when we go to that acetaldehyde, it has 1 CH3 group. What the plus I group will do? It has to release the electron towards the carbon atom. See, I have CH3, CHO, as well as I can take the ketone. So both of these plus I group, you know, that releases the electron towards the carbonyl carbon. Because of the plus I effect, electron releases towards the carbonyl carbon. Actually, the carbon electron density must be smaller, then only nucleophile can approach. But the release of electron from the alkyl group to the electrophilic site, that increases the electron density on carbon plus ion, that is electrophilic site, and hence the electrophilicity decreases, the approach of nucleophile will be restricted. So when the alkyl group releases its electron towards that carbonyl carbon, the electron density of carbonyl carbon increases and hence electrophilicity decreases. So this is the reason why acetone that take part in nucleophilic addition reactions less favored compared to formaldehyde or acetaldehyde. That's all the reactivity of aldehydes and ketones that can be explained on the basis of steric reasons and electronic reasons. Let us see one by one how the nucleophilic addition reaction takes place in both aldehydes and ketones. The first nucleophilic addition reactions with hydrogen cyanide. This hydrogen cyanide, when it is in pure, the reaction will be very slow. So to make the reaction faster, actually hydrogen cyanide is treated in a base medium. So the presence of base, it may facilitates to produce the cyanide ion. This cyanide ion is the nucleophile in which the carbon carries the negative charge with a pair of electrons. So when the cyanide it approaches the carbon atom, we may find the oxygen withdraws the electron and the cyanide approaches the electrophilic site. We are getting the anionic form of addition product. And this oxoanion that abstract the proton from the reaction medium, so we are getting cyanohydrine as the product. So it is acetaldehyde cyanohydrine. Cyano for CN group, hydrine for the OH group. And this cyanohydrine that behaves as a very good synthetic intermediate, because the cyano group that can undergo hydrolysis, it may undergo partial hydrolysis as well as complete hydrolysis. When it undergoes complete hydrolysis, the cyano group that can be converted into carboxylic group. So we can able to convert the carbonyl compound into hydroxycarboxylic acids. That's why it is said to be synthetic intermediates. So during the hydrolysis of CN group, actually 2 molecules of water will be taken, where CN group is converted into COOH and the nitrogen will be left as ammonia. Here the compound formed is lactic acid. Or you can say this is the carboxylic acid 1, 2, 3. It is 2-hydroxypropanoic acid. It is 2-hydroxypropanoic acid. Similarly, we can take acetone. In this also, the cyano group approaches the electrophilic site, so we are getting this ion, and this abstract the proton from the reaction medium, so we are getting cyanohydrine. It is acetone cyanohydrine. Followed by hydrolysis, once again the cyano group is converted into carboxylic group, so we are getting hydroxycarboxylic acid. In this, instead of hydrogen, a methyl group is present at the second position, so we can write this is first position, second position, third position. So it is 2-methyl propanoic acid. So it gives 2-hydroxy-2-methyl propanoic acid. This conversion is important because they may ask you to convert acetaldehyde into lactic acid. These are the reactions. Most of the time they proceed in reversible manner. And the first step of the reaction will always be slow, but the following step will be faster. So the addition of cyano group, that will be slow process, but the abstract of proton from the reaction medium becomes a fast step. So it is slow and this will be fast. That's all. Nucleophilic addition reaction of hydrogen cyanide to acetaldehyde and acetone. Acetaldehyde can be converted into lactic acid. Likewise, this acetone can also be converted into hydroxycarboxylic acid, followed by the hydrolysis of cyanohydrine. Addition of sodium hydrogen sulfide to carbonyl compounds. This method is very much useful for the separation of the pure form of carbonyl compound because the formation of the addition product that becomes water soluble. So this can be recovered. The original carbonyl compounds can be recovered in pure form by treating with either dilute acid or with dilute alkali. So let us proceed how the reaction carried out in carbonyl compound. This sodium hydrogen sulfide is a salt of sulfurous acid. Sulfurous acid is H2SO3, that is also a dibasic acid. So in this H2SO3, one of the hydrogen is replaced by the sodium. That's why we are getting the sodium salt of sulfurous acid called sodium hydrogen sulfide. In this, the oxygen that attacks that sodium, subsequently that sulfonic group attacks the carbon. We are getting that compound by which the proton transfer takes place among this SO2OH group and ONA group. So we are getting sodium bisulfite addition product. It is called sodium bisulfite addition product. Why it is called bisulfite? We can say NaHSO3 as sodium hydrogen sulfide as well as sodium bisulfite. Both of them are similar. Also we can find this reaction in ketone the same manner and from which the water soluble products are obtained. So when we discuss about that equilibrium position of aldehydes and ketones, in aldehyde, the reaction equilibrium always lies to the forward direction, but in ketone, the position of equilibrium lies to the reactant side. This is why, because the steric reason, because the carbonyl group, it has two methyl subgroup in the acetone as well as the sodium bisulfite is such a bulky group. Because of the steric nature of the alkyl group with the nucleophile, the position of equilibrium always lies left to the reaction when with ketone. But in the case of aldehyde, position of equilibrium always lies towards the formation of product because this carbon, it has only one methyl group and it finds less steric effect. The next nucleophilic addition reactions of carbonyl compounds is with the Grignard reagent. With respect to the carbonyl compound, what we have selected, based on that we can get primary, secondary and tertiary alcohol. About this already we have discussed in two of the cases, one in halogen derivatives, the other one in alcohol chapter. Let me share the link for this reaction, we can find it. The next let us go to with addition of alcohol. Alcohol, a monohydric alcohol or a dihydric alcohol can be taken, but monohydric alcohol that prefers to undergo reaction with the acetaldehyde and the dihydric alcohol undergoes reaction with the ketone. As a result of this, aldehydes will give hemiacetals and acetals, but ketones will give ketols. Let us discuss first of all with the acetaldehyde with methanol. So CH3OH is methanol and the reaction must be carried out in presence of dry HCl. Why? This dry HCl only able to protonate that oxygen atom of carbonyl group and hence the electrophilicity of carbon increases. So the nucleophilic attack can be facilitated upon this. So dry HCl is must for this. So we can say this oxygen that can be protonated by the methanol group. So we can proceed the reaction, oxygen that is protonated with the methanol and the oxygen atom of methanol approaches the carbonyl carbon. We are getting this compound, it is called hemiacetal. And this hemiacetal you can name it as, it is actually ethanol, 2 carbon. Ethanol. In ethanol, one of the hydrogen by methoxy group. So we can write it as methoxyethanol. The name of the compound is methoxyethanol, alcoholic compound. It can undergo the reaction with one more molecule of methanol in presence of dry HCl. Here also the OH group of this compound will protonate with methanol, and hence there is a loss of water molecule minus H2O. Subsequently, the CH3O group that can add with this carbon, we are getting dimethoxyethane. It is a gem alkoxy group. Because to the same carbon, the alkoxy groups are present, that's why it is called gem alkoxy. The name of the compound is dialkoxymethoxyethane. Dimethoxyethane, because it has 2 carbon atom and hence it is ethane. Then with acetone, acetone undergoes nucleophilic addition reaction with ethylene glycol, a dihydric alcohol. This is also the dry HCl helpful to protonate that carbonyl oxygen with the hydrogen atom of alcohol, and hence there is a loss of water molecule. So the doubly bonded carbon that can easily attached with the CH2O minus group of ethylene glycol. So we are getting ketols. It is ethylene glycol ketol. And the carbonyl compound that can be immediately recovered when this acetal or ketols treated with mineral acid. Oxidation of carbonyl compounds. Acetaldehyde and acetone taken, but we can write the formulas even as the general one, RCHO or RCO R dash. Just to facilitate the understanding, I have taken the specific compound, but the alkyl group could be any of the alkyl group. So during the oxidation of aldehyde, it gives carboxylic acid. And aldehydes, they are ready to undergo oxidation even in presence of the strong oxidizing agent as well as mild oxidizing agents. The strong oxidizing agents are concentrated nitric acid, alkaline potassium permanganate, or even acidified potassium dichromate. The mild oxidizing agents are Tollens reagent and filling solutions. So aldehydes, they can undergo oxidation even in presence of mild oxidizing agent, and they too form carboxylic acid, and in this case you can find the retaining of number of carbon atom with the aldehyde and acid. That's why I have taken the particular compound for this process. See, I have 2 carbon in aldehyde and I may find 2 carbon in carboxylic acid also. But in the case of ketone, I have taken acetone. This can be oxidized only by strong oxidizing agents such as potassium permanganate or dichromate or nitric acid, the concentrated one. When you consider the ketone, we have the 2 types. One is symmetrical ketone, the other one is unsymmetrical ketone. The symmetrical ketone, it doesn't find any difference in their oxidation because the cleavage of carbon-oxygen bond that take place exactly between CO group. So here or here you may find. So in case of symmetrical ketone, the CO group, the cleavage of the bond between carbonyl and carbon takes place, and hence this CH3CO, when it is oxidized, I am getting CH3COOH. What about this alkyl group? The alkyl group actually oxidized to formic acid, but due to the presence of strong oxidizing agent, this undergoes further oxidation to form carbon dioxide and water. So upon the oxidation of ketone, you will find carboxylic acid, but there would be a loss of 1 carbon in its product. See, here I have 3 carbon atom, but in carboxylic acid I have only 2 carbon atom. Okay. In the case of unsymmetrical ketone, the cleavage of carbon between the carbonyl group and the alkyl part takes place according to Popoff's rule. This Popoff's rule, it states that during the oxidation of unsymmetrical ketone, the ketonic group should always stay with smaller alkyl group. So in this unsymmetrical ketone, I may find that the two possibilities of cleavage of carbon and carbonyl group. One is C1C2, the other one is C2C3. But according to Popoff's rule, the carbonyl group should stay with smaller alkyl part, not with the longer. So as according to the Popoff rule, the cleavage of carbonyl and oxygen takes place between C2 and C3 carbon. So this 3 carbon, that is the propyl group, oxidizes into propanoic acid, and that acetyl CH3CO group, that is into acetic acid. So we are getting propanoic acid and acetic acid. Oxidation of aldehydes and ketones with mild oxidizing agents. Already I discussed about the mild oxidizing agents are Tollens reagent and Fehling solution. Tollens reagent is actually an ammoniacal solution of silver nitrate. Ammoniacal, that is nothing but the presence of ammonium hydroxide. That means silver nitrate is taken in ammonium hydroxide solution. So in this case, when silver nitrate is placed in ammonium hydroxide, that forms the complex of the type AgNH3 twice plus. It is actually diamine silver plus ion and OH minus ion. So this is what to be taken as the reagent for the chemical reaction. And what is called a Fehling solution? Fehling solution is a mixture of Fehling A and Fehling B. Fehling A is only the aqueous solution of copper sulfate, but Fehling B is an alkaline solution of sodium potassium tartrate. That sodium potassium tartrate is also known as Rochely salt. So when copper sulfate present in alkaline solution of this Rochely salt, the reagent is usually taken as copper 2 plus ion in OH minus, because in copper sulfate, copper is present in its plus 2 oxidation state. Okay, and these two reagents are being mild oxidizing agents. We know well ketones do not undergo, because ketones require the strong oxidizing agent. So only the aldehydes may answer for Tollens test and Fehling solution, and hence these two tests are taken as the method of distinction between aldehydes and ketones. Moreover, we have aliphatic aldehyde as well as aromatic aldehyde. Say acetaldehyde and benzaldehyde I have taken. This Tollens test that can be answered for both acetaldehyde and benzaldehyde, but the Fehling test can be answered only for the aliphatic aldehyde, not for aromatic aldehyde, because the presence of the strong alkaline solution, say sodium hydroxide, that makes this reactant benzaldehyde to undergo disproportionation reaction. Disproportionation reaction means that benzaldehyde undergoes oxidation and reduction takes place in the same compound, that is called the disproportionation reaction. So you can take both aliphatic aldehyde and aromatic aldehyde for Tollens test, Fehling's test only for aliphatic aldehyde. Why not for aromatic aldehyde? Because aromatic aldehyde that will undergo disproportionation reaction, and hence it does not answer for the test. This is because the presence of strong alkali in the reaction mixture. Okay, let us find the acetaldehyde CH3CHO with the Tollens reagent. A Tollens reagent to be represented as diamine silver plus ion and OH minus. In this case, the acetaldehyde, the aldehyde is oxidized to carboxylic acid, and this Tollens reagent is reduced to silver mirror. We may find the deposition of silver around the glass tube at the bottom of it. So that is observed as silver mirror. So the Tollens reagent test can also be termed as silver mirror test. So in this case, the silver, diamine silver ion is reduced to silver and ammonia along with water. At the same time, when we take acetaldehyde with Fehling's test, here the copper 2 plus ion is reduced to copper 1 oxide. 2 plus is reduced to copper 1, that is plus 1 state. So the formation of copper 1 oxide that makes red precipitate of the reaction product. So from the result of either the red precipitate or the silver mirror, you may say the compound is aliphatic aldehyde. Aromatic aldehyde that produce the silver mirror but do not form red precipitate with the filling solution. So let us balance the reaction. In the first case, acetaldehyde is oxidized to acetate ion, that is the carboxylic acid. And you may find here the 2 oxygen with the water, 1 oxygen. And moreover, not only the number of atoms, the charges to also be balanced. So here the product side I have 1 negative charge, but the reactant side plus and minus that makes cancel it. So to get the resultant of 1 negative charge and to make the number of oxygen to 3 times, I can take this is as 3 times. So 3 minus, I need to take only 1 minus. So subsequently I am going to multiply this is by 2 times. Now you find 3 minus 2 plus, the resulting is minus 1. So I am getting the negative charge to the product side. This is just for balancing the number of oxygen. 3 oxygen plus 1, 4 oxygen. So here I have 2, water also 2 times because of 3 hydrogen plus 1 hydrogen, 4 hydrogen. And silver 2 times, so it is 2 Ag, and ammonia 2 2s are 4, so ammonia becomes 4 times. When you have it with filling solution, copper 2 plus is reduced to copper 1 oxide where you are finding 2 times of copper. So this is, we take it as 2Cu2 plus. And the resulting charge, right side I have minus 1, but left side 2 2s are 4 plus, minus, that makes 3 plus. So to balance the number of charge, I am going to multiply this OH with 5 times. So 4 plus 5 minus, then resultant is minus 1, product side also minus 1. Let us balance the number of oxygen, 5 oxygen plus 1, 6. Here I have 2 and 5 hydrogen plus 1, 6 hydrogen. So here there are 3 molecules of water. So out of 6 oxygen, 2, 3, 3 plus 3, 6. So this is what the balanced. In such cases, we have to balance the reaction because it involves the ions in the reaction. In general, the all organic reactions are, they can say no need to balance. But better balance the reaction as far as possible because we no need to that lose the marks and all. And if you consider the ionic reaction, the balancing is compulsory. That's all. Oxidation of aldehydes with Tollens reagent and filling solution. Reduction of carbonyl compounds. This reduction that can be carried out with either of the reducing agents like sodium borohydride, lithium aluminum hydride, or the catalytic reducing agents of nickel hydrogen, platinum hydrogen, or palladium hydrogen. In such reduction, the carbonyl group is converted into CHOH. The carbonyl C double bond O is reduced to CHOH. So the addition of hydrogen takes place between the carbon and oxygen. So depends on the nature of the carbonyl, you may get the primary alcohol or secondary alcohol. Usually aldehyde gives the primary alcohol and ketone gives a secondary alcohol. Let us take aldehyde as well as ketone by choosing sodium borohydride as a reducing agent. Here the CO group is reduced to CHOH group. So we are getting the primary alcohol CH3, CH2OH. In the case of ketone, the CO group is reduced to CHOH group. So we are getting secondary alcohol. So the reduction of aldehyde gives primary and that of ketone gives secondary alcohol. So in this case, the carbonyl compounds are converted into alcohols. But we have one more method of reduction in which the carbonyl group is converted into the alkyl part, that is the methylene CH2 part, and that can be brought by two different reactions. One is called Wolff-Kishner reduction. So carbonyls are converted into hydrocarbon by Wolff-Kishner reduction. In this, the reducing agent is hydrazine and potassium hydroxide in glycol or potassium hydroxide in ethanol or potassium ethoxide that behaves as a catalyst. So this reaction it undergoes in presence of a catalyst like a potassium hydroxide in glycol or potassium hydroxide in ethanol. So in this case the CO group is converted into first of all the nucleophilic addition elimination reaction. See this oxygen that is removed as water with the NH2 group of one of the NH2 group of hydrazine. So we are getting this product. It is called hydrazone actually, and this hydrazone upon the presence of catalyst that converts the C double bond into CH2 N2 along with water. So let us have the specific examples of acetaldehyde and acetone. So the first step, there is the formation of hydrazone when the removal of water takes place between the aldehyde and the hydrazine. So hydrazone is formed, and this hydrazone it undergoes reduction by the catalyst. So we are getting the CH into CH3 N2 plus H2O. So this part CH3 CH part is converted into CH3. So ethanol into ethane. Similarly, propanone. Here also the oxygen atom of the carbonyl group that is removed as water. So you are getting acetone hydrazone. And further reduction, this CH3 C double bond CH3 is into CH3 CH2 CH3. We are getting propane. So propanone gives propane and ethanol gives ethane. This is Wolff-Kishner reduction. In this you should remember the reducing agent is hydrazine and the catalyst is alkali present in alcohol. In addition to Wolff-Kishner reduction reaction, Clemmensen reduction also converts carbonyl compound into hydrocarbon. But in Clemmensen reduction, we have to take zinc, mercury, amalgam and concentrated hydrochloric acid. Because of this, it can provide the 4 hydrogen atom. Nothing, the zinc reacts with the HCl to form zinc chloride and hydrogen. That hydrogen is utilized for the reduction of CO group into CH2 group. Already we have one hydrogen, so that makes CH3. So ethanol into ethane. And also the acetone, that is the propanone, is converted into propane with Clemmensen reducing agent of zinc, mercury, amalgam and con HCl, where the oxygen atom of this carbonyl group is left as water molecule. So here also the CO group is converted into CH2. We are getting propane from propanone and ethane from ethanol. Besides these two reduction reaction, we have one more reaction where the ketones are converted into symmetric diols, that is said to be pinocols. So we can consider reduction of ketones to pinocols. In this case, the reducing agent is actually magnesium amalgam and water. In Clemmensen reduction, we use the zinc amalgam with the con HCl, but in the case of pinocols reduction, we have to take magnesium amalgam and water. So how the reaction proceeds? We have to take that 2 molecules of acetone. First of all, this acetone that forms an addition complex with magnesium. So we are getting the magnesium addition complex. So both of the double bond, magnesium its valency, that is 2 plus, and oxygen both of them are minus. So and hence you may find the movement of the electron that makes like this. That's why the 2 carbonyl group of separate acetone that make carbon-carbon single bond, and the formation of this that makes addition complex with the magnesium, followed by hydrolysis. We can take water, we may find the Mg it combines with the OH, and the minus, the oxygen will combine with the hydrogen. We are getting diol to the adjacent carbon atom of compound. So this is called pinocols. and in which the two OH groups are at the adjacent position, and above the OH group you may find the two alkyl groups are present, and hence it is said to be symmetric diols, and these are vicinal diols also. Why? The OH group are at the adjacent carbon atom. So ketones that can also be converted into pinacols in the presence of magnesium amalgam and water. So okay, let us continue this chapter in our next session. Until then, bye bye.